Hello, and welcome to this quiet journey through the cosmos. Before we drift into the mysteries of time, make sure to subscribe so you don't miss any of these calm, science-filled explorations. Tonight, we'll gently travel through space to discover why time moves slower when gravity pulls or motion speeds past, following real experiments, observations, and precise science. From orbiting satellites to distant black holes, you'll see how the universe subtly shapes every second. So, take a deep breath, relax, and let your mind float among the stars as we begin uncovering the secrets of time. You feel the rhythm of your day, a quiet cadence built from seconds and minutes. The morning light shifts gradually across your room, unnoticed at first, yet steady. Clocks tick with familiar precision, their hands moving at a rate you trust. Your mind experiences time as a constant stream, a steady flow that organizes thought, activity, and memory. Every heartbeat, every breath, marks a tiny fraction of this passage, and your senses merge it seamlessly with your awareness of the world. Yet even as time seems so uniform, careful observation begins to reveal its subtleties. Human perception of time is inherently linked to the cycles of your planet. The rising and setting of the sun traces Earth's rotation, completing one full turn every 24 hours. Days and nights shape not only light and shadow but also the biological rhythms of living beings. Your body's circadian clock synchronizes with this rotation, governing sleep, hormone release, and alertness. It adapts slowly, yet reliably, to seasonal changes, demonstrating a deep connection between life and planetary motion. These cycles are remarkably precise, yet they are only a human-scale reflection of a far larger system of time itself. Timekeeping, in its most practical form, began with simple observation of the skies. Ancient humans noticed repeating patterns in sunlight and stars. They marked days, months, and years by tracking these celestial motions. Over millennia, these observations evolved into mechanical devices capable of more consistent measurement. Clocks and calendars allowed societies to plan, organize, and coordinate activity, all by measuring intervals of the passage of time. You follow this history quietly, aware that the tools humans have created are fundamentally attempts to measure something elusive, a phenomenon that is felt universally but understood with growing precision. The development of mechanical clocks introduced new ways of observing subtle differences in time. Pendulums swing at constant rates, and gears turn predictably, yet even these early instruments are affected by gravity, temperature, and friction. Time, though appearing steady, exhibits small variations when measured carefully. You imagine a pendulum swinging in a quiet room, noting that its rate depends on the strength of gravity where it hangs. This realization quietly expands your awareness. Time, as measured, is sensitive to environmental factors, even here on Earth. In modern science, the measurement of time reaches remarkable precision through atomic clocks. These clocks count the vibrations of atoms, often cesium or rubidium, as they shift between energy levels. Each oscillation occurs with astonishing regularity, allowing time to be measured with accuracy down to billionths of a second. Observatories and laboratories use these clocks to synchronize global systems, from telecommunications to GPS satellites. You appreciate the subtlety in this accuracy. A fraction of a second may seem inconsequential in everyday life, yet it represents the most precise understanding humans currently achieve of time's progression. Even on Earth, experiments detect tiny differences in the passage of time. Clocks positioned at different heights tick at slightly different rates due to variations in gravity. A clock on a high mountain moves imperceptibly faster than one at sea level. These differences, measured in nanoseconds per day, confirm that time is not entirely uniform. The effect is minute, yet it is real and observable. You sense a gentle wonder in this knowledge. The flow of time you experience is closely connected to your position within Earth's gravitational field, reminding you that time interacts with the physical world in ways you may rarely notice. Your daily routine, structured around minutes and hours, also reveals the subjective side of time. Moments of attention, focus, or relaxation can seem to stretch or contract the passage of time. You remember hours spent reading, absorbed in thought, which felt brief, and evenings that lingered slowly in wakefulness. While perception and measured time are distinct, they are interconnected. Your experience is shaped by both physiological processes and external cycles, illustrating that even before considering the cosmos, time has layers of complexity that influence your consciousness. Astronomical observations extend this understanding beyond Earth. You note that Earth completes an orbit around the Sun in a little over 365 days. This orbital period, combined with the planet's rotation, structures the calendar, seasons, and longer cycles of time. Over millions of years, these patterns remain consistent, yet slight variations, such as the gradual slowing of Earth's rotation due to tidal friction, subtly alter the length of a day. Time, therefore, is not only measured by instruments but also by celestial motion, linking your immediate experience to the larger rhythms of the planet and solar system. Looking at the night sky, you see stars and planets moving along predictable paths. Their motions are so consistent that they have been used for navigation for centuries. Ancient astronomers could predict eclipses, track the positions of planets, and anticipate seasonal changes. Today, telescopes allow you to measure these movements with extraordinary precision, confirming that the cosmos itself follows a temporal order. Each orbit, rotation, and revolution contributes to the structure of time across vast distances, and your understanding deepens as you connect human-scale clocks to the immense scales of space and motion. Even the perception of simultaneity is not absolute. Experiments with light and precise timing reveal that events occurring at different locations may be measured differently depending on distance and the observer's motion. Your mind considers that the simple flow of seconds on Earth is already embedded within complex relationships of position and movement. Light takes time to travel across space, and your observation of distant events is always slightly delayed. You notice that the familiar feeling of now is intertwined with the finite speed of information and the structure of space itself, a subtle but profound connection between perception and physical reality. As you reflect on the quiet ticking of clocks, the rising sun, and the measured rotations of Earth, you begin to understand that time is both intimately familiar and surprisingly intricate. It governs your life, structures your thoughts, and yet remains a phenomenon that is measured, tested, and refined through careful observation. Its flow is sensitive to environment, position, and motion, even if these differences are imperceptible in your daily routine. The world around you, from your heartbeat to the orbiting planets, participates in this rhythm, connecting the personal and the cosmic in ways that are precise and measurable. You feel a gentle awareness that while your experience of time seems constant, it is shaped by physical laws and measurable effects. Even within the room you occupy, subtle variations exist, quietly linking your life to planetary rotation, gravitational forces, and the movement of Earth through space. The simplicity of a clock ticking hides the depth of science behind each second. You sense that these patterns, though subtle, hint at a wider reality. Time is not a single, universal flow but a phenomenon influenced by motion and gravity, a discovery that invites you to explore how this flow changes beyond the surface of your familiar world. You begin by noticing the clocks around you, each quietly measuring the passage of seconds. Their hands move at a regular pace, a comforting rhythm that organizes your day. Mechanical clocks, with their gears and pendulums, were once marvels of precision. A swinging pendulum regulates the movement of gears, translating its steady oscillation into the familiar tick-tock that marks moments. The accuracy of these devices depends on careful calibration and on the pull of gravity, which subtly influences the pendulum's period. Even small changes in the length of the pendulum or the strength of gravity can alter the measured time, reminding you that precision is never absolute. As technology advanced, human curiosity sought greater exactness. Quartz clocks replaced pendulums, using the vibrations of a crystal under an electrical current to maintain a precise oscillation. These vibrations are regular to millions of cycles per second, allowing time to be measured far more accurately than with purely mechanical devices. You imagine a crystal vibrating silently, its motion invisible to the eye, yet each tiny oscillation contributing to the orderly tracking of seconds. In these clocks, you see the beginning of humanity reaching toward time measurement limited only by the natural laws that govern matter and energy. Your understanding deepens as you encounter atomic clocks. These clocks rely on the predictable energy transitions of atoms, often cesium or rubidium, as electrons shift between defined energy levels. Each transition emits electromagnetic radiation at a consistent frequency, which can be counted to maintain a highly stable measurement of time. Atomic clocks can measure time with accuracy to billionths of a second per day. You sense the quiet rigor of science in this precision. Each tick of an atomic clock is an observable, repeatable phenomenon, independent of mechanical imperfections or environmental noise. Experiments using atomic clocks have revealed subtle yet profound aspects of time. When two identical clocks are positioned at different altitudes, even a few meters apart, they tick at slightly different rates. A clock placed higher above Earth's surface runs faster than one closer to sea level. This effect is a direct result of gravitational time dilation, predicted by Einstein's theory of general relativity. The difference is small but measurable, demonstrating that even on Earth, time is not uniform. You feel a gentle awareness that each passing second carries the imprint of physical laws, connecting you to the planet in a precise and quantifiable way. Precision in observation is central to understanding time. Scientists have synchronized atomic clocks across continents, comparing their rates to detect even the smallest discrepancies. Lasers and optical fibers transmit signals with extreme accuracy, allowing the comparison of clocks separated by thousands of kilometers. These experiments confirm that time can be measured reliably, yet also reveal its sensitivity to motion, gravity, and environmental factors. You imagine the quiet collaboration of scientists and instruments, each contributing to an ever more refined understanding of how time behaves in the physical world. Your mind turns to the practical applications of this precision. Satellite navigation, for instance, depends entirely on accurate timekeeping. Signals sent from orbiting satellites include precise timestamps, which receivers use to calculate position. Even nanosecond errors would translate into meters of navigational uncertainty. The exactness of atomic clocks ensures that technology functions seamlessly, while also reflecting fundamental truths about the nature of time itself. You notice how intertwined observation and measurement are, bridging everyday life with the subtle, universal patterns that govern temporal flow. Timekeeping is not only about counting seconds but also about understanding their variability. Experiments have shown that motion affects clocks, a phenomenon known as time dilation. Moving atomic clocks tick more slowly relative to stationary ones, a prediction verified repeatedly with aircraft, satellites, and particle accelerators. The behavior of these clocks, observed with exacting care, provides direct evidence that time is influenced by velocity, not merely by perception. You consider the profound implication that time is not an absolute background but a measurable quantity shaped by physical context. Observations extend beyond Earth. High-precision clocks aboard spacecraft and satellites allow scientists to test relativity across different gravitational potentials and velocities. Comparisons with ground-based clocks reveal differences that, while tiny, are consistent with theoretical predictions. You follow the quiet logic of these experiments, appreciating the rigor with which scientists isolate variables and account for effects. Each measurement reinforces the understanding that time is a physical dimension, responsive to the same forces that govern motion, mass, and energy. You notice that observation itself requires patience. Even the most precise instruments must be calibrated, shielded from environmental disturbances, and maintained over long periods to provide meaningful data. Time measurement becomes both an art and a science, blending human ingenuity with the predictability of atomic and quantum systems. The interplay between instruments and laws of nature reveals a subtle harmony. Time is consistent enough to measure, yet flexible enough to reflect variations caused by gravity, motion, and relative position. As you reflect on the quiet work of these clocks, you sense the importance of careful measurement in revealing deeper truths. Each tiny tick, each vibration of an atom, contributes to an understanding that time is not merely a human construct but a real, measurable phenomenon. It responds to motion and gravity, and its behavior is predictable, observable, and experimentally verified. You feel a calm confidence in the reliability of science, and a gentle curiosity about how these patterns extend beyond Earth's surface. Your awareness begins to extend toward the cosmos, imagining time flowing differently where gravitational fields vary and velocities reach extremes. You sense that the careful observation of time on Earth is only the beginning, a foundation for understanding how seconds stretch and compress across the universe. The precision of clocks, the discipline of measurement, and the consistency of atomic behavior all reveal a quiet, orderly structure underlying the flow of moments, hinting at the intricate relationship between time, space, and motion that you will gradually explore. You feel the familiar rhythm of your surroundings and begin to consider time in a broader sense. On Earth, seconds, minutes, and hours pass predictably, yet careful measurement already hints that this passage is sensitive to position and motion. To understand why, you turn to the work of Albert Einstein, whose observations and reasoning reveal that time is not an independent, universal flow but part of a four-dimensional continuum called spacetime. In this view, space and time are inseparably linked, and the structure of one affects the other. Your mind follows the simplest idea first. The speed of light is constant. Light travels at the same rate for every observer, regardless of motion or reference point. This constancy seems subtle, but it has profound implications. If the speed of light cannot change, then measurements of space and time must adjust depending on the observer's motion. You imagine a beam of light moving across a room, its journey unaltered by your own movement, and notice that the rules governing light impose limits on how time and space interact. Einstein's special relativity formalizes this relationship. You learn that as an object approaches high velocity, close to the speed of light, time for that object slows relative to a stationary observer. Moving clocks tick more slowly than those at rest. This effect, called time dilation, is not hypothetical. It has been confirmed in countless experiments with particles, spacecraft, and precision instruments. You feel the quiet certainty of measurement, noticing that these results emerge consistently whenever motion is extreme, revealing a fundamental property of the universe rather than an artifact of perception. You reflect on how motion alters the experience of time. In everyday life, you move at speeds so small compared with the speed of light that these effects are imperceptible. A running person or a moving car experiences no measurable difference from someone standing still. Yet particles in accelerators, moving at over 99% of the speed of light, demonstrate significant slowing of their internal clocks. Lifetimes of unstable particles extend, collisions behave differently than would be predicted by Newtonian mechanics, and every observation confirms that the rules of special relativity accurately describe high-speed phenomena. Time and space are intertwined in another way. Lengths contract along the direction of motion, an effect known as length contraction. Just as moving clocks tick slower, moving objects appear shorter along their path when observed from a stationary frame. You notice that this is not an illusion but a consistent consequence of the underlying structure of spacetime. The two effects, time dilation and length contraction, work together to preserve the constant speed of light. They are measurable and predictable, forming a precise mathematical framework that governs motion at high speeds. Gravity introduces an additional layer of complexity. Einstein's general relativity extends the concepts of special relativity to include accelerated motion and gravitational fields. Massive objects warp spacetime, bending both the path of moving bodies and the flow of time. A clock positioned near a massive planet or star runs slower than a clock farther away. This effect, called gravitational time dilation, has been confirmed by placing atomic clocks at varying altitudes and observing their relative rates. You perceive the subtle connection. The geometry of spacetime, shaped by mass and energy, directly influences the rhythm of time. Observations in Earth's orbit provide tangible examples. Satellites experience weaker gravity than clocks on the planet's surface, causing their time to pass slightly faster. Simultaneously, their high velocity slows their clocks. The combination of these effects is measurable and must be corrected in applications such as GPS, which rely on precise timing to calculate positions. You sense that the flow of seconds is not simply a local experience but a dynamic phenomenon influenced by motion and mass, detectable with careful instruments and essential to technological systems. The constancy of the speed of light leads to further consequences for simultaneity. Events that appear simultaneous from one reference frame may not be simultaneous from another moving frame. Your awareness of now is relative to your own position and velocity. This does not mean that reality is uncertain. Rather, it is structured differently than intuitive, absolute notions of time would suggest. Scientists verify these predictions through experiments involving synchronized clocks, particle collisions, and precise astronomical observations. Each test confirms that time and space form a unified, measurable continuum. You notice that these effects, though subtle at everyday speeds, accumulate at larger scales or higher velocities. Even small differences in time experience during motion or in varying gravitational fields can become significant when applied to spacecraft or long-duration experiments. Astronauts on the International Space Station age slightly less than people on Earth over the same period, an effect calculated from both their velocity and the weaker gravitational field they experience. You feel a quiet wonder at how fundamental laws of physics subtly shape human experience and biological reality, even if imperceptibly. Experiments with particle accelerators offer another perspective. Particles accelerated to near-light speeds decay more slowly than identical particles at rest. These observations match precisely the predictions of special relativity, confirming that the behavior of matter at extreme velocities follows the principles Einstein described over a century ago. The evidence is robust and repeatable, not speculative. You recognize that time itself is flexible, measurable, and influenced by the physical context in which objects exist. Light from distant stars and galaxies provides further confirmation. The travel time of photons across space, combined with observations of astronomical events, demonstrates that the speed of light is constant and that time behaves predictably across cosmic distances. Redshift measurements, pulsar timing, and orbital dynamics all provide independent verification of relativistic effects. You notice how these patterns link the familiar experience of seconds on Earth to the larger cosmic environment, showing that the rules of spacetime apply universally and consistently. Even in daily life, the principles are quietly at work. GPS systems, satellite communications, and scientific measurements all account for relativistic effects. Engineers correct for both velocity-induced and gravity-induced time dilation to ensure accuracy. The consistency of these corrections across systems and experiments provides continual verification of the relationship between motion, gravity, and the passage of time. You sense the seamless integration of abstract physics with practical application, reinforcing the understanding that time is a measurable, malleable dimension of reality. You reflect on the elegant simplicity underlying these complex phenomena. Despite the mathematical precision and technological sophistication required to measure them, the principles themselves are clear. Time and space are intertwined, motion slows clocks, gravity warps the flow of moments, and the speed of light remains constant. Each observation reinforces the coherence of the universe, revealing a structure that is both subtle and profound. You feel a quiet calm in knowing that these truths are accessible through patient measurement and careful reasoning. Your attention lingers on the flow of seconds around you, recognizing that time is not uniform but influenced by both speed and gravitational field. Each tick of a clock is not only a marker of your immediate experience but also a reflection of a broader cosmic framework. This understanding invites curiosity about how these variations in time manifest in extreme environments, where velocities approach the speed of light and gravitational forces reach the limits of what we can measure. You sense that the universe is organized in a way that allows such measurements, offering a continuous path to explore the relationship between motion, gravity, and the rhythm of time. You feel the pull of gravity even as you sit quietly, a subtle force anchoring you to Earth. Gravity is familiar in its effects on motion, balance, and weight, yet its influence extends beyond the physical pull you sense. It shapes the very rhythm of time itself. Clocks positioned in different gravitational fields tick at slightly different rates. You imagine two identical clocks, one at the base of a mountain and one near its summit. Over the course of a day, the higher clock runs imperceptibly faster than the lower one. This is not speculation but observation, a measurable consequence of the warping of spacetime caused by mass. Einstein's general relativity provides the framework to understand this effect. Mass curves spacetime and objects, including clocks, move along paths determined by this curvature. A clock deep in a gravitational well experiences slower passage of time relative to a clock positioned farther away. On Earth, the differences are tiny, detectable only with atomic clocks, yet they demonstrate a fundamental principle. Gravity influences the flow of time. You sense the quiet subtlety of this phenomenon, feeling that time is both familiar and flexible, shaped by the invisible contours of mass surrounding you. Experiments with atomic clocks at varying altitudes confirm this effect with precision. Scientists have placed ultra-precise clocks at the tops and bottoms of tall towers, mountains, and deep valleys. Each measurement reveals that the higher clock gains time relative to the lower clock, a direct confirmation of gravitational time dilation. Even a difference of a few meters produces a measurable result. You notice that the seconds ticking by around you are not entirely uniform. Their flow is subtly entwined with your position in the gravitational field. Satellites provide another clear demonstration. Orbiting clocks experience weaker gravity than those on Earth's surface, and therefore time for them passes slightly faster. These differences are not merely academic. They are essential for practical systems such as GPS. The position calculations for satellites must account for the combination of gravitational and velocity-related time dilation. If these corrections were ignored, navigational errors would accumulate rapidly, demonstrating that relativity has tangible, observable consequences in technology you rely on. Gravity also influences light, further illustrating the connection between mass and time. Light passing near a massive object is deflected, an effect known as gravitational lensing. Although the speed of light remains constant locally, the path it follows bends, and the time it takes to travel can be slightly altered by the curvature of spacetime. Observations of starlight around the sun during eclipses first confirmed this effect over a century ago, and modern instruments have measured it across galaxies. You feel a quiet reassurance that these effects, though imperceptible to human senses in daily life, are detectable and predictable through careful observation. Closer to home, subtle effects of gravity on time can accumulate over long durations. Even the difference of a few billionths of a second per day becomes significant over years or decades. Long-term measurements with atomic clocks at various altitudes, combined with spacecraft telemetry, reveal that gravity continuously modulates the passage of time. You notice that every moment is influenced by this invisible structure of spacetime, linking your immediate experience to universal principles of physics. Gravitational time dilation is strongest near extremely massive objects. Neutron stars and black holes produce intense gravitational fields, slowing time drastically for nearby observers. Light emitted from these regions is redshifted, stretching to longer wavelengths as it climbs out of the gravitational well. Observational astronomy confirms these predictions, revealing precise shifts in timing and frequency that match the calculations of general relativity. You consider that even the familiar experience of seconds on Earth is part of a continuum influenced by mass, motion, and energy across the universe. Even everyday actions reveal the subtle effects of gravity on time. When you climb a staircase or travel to higher ground, your change in altitude results in a minuscule increase in the passage of time for your position relative to someone remaining at the original height. The difference is unimaginably small, yet it is real and measurable with sensitive equipment. You sense the quiet, pervasive influence of gravity. It shapes both motion and time, always present, always exerting its effect in ways you rarely notice. Observational evidence extends to spacecraft journeys. Probes traveling to planets, moons, or distant asteroids experience variations in gravity along their trajectories. Onboard clocks record these changes, providing empirical data that align precisely with theoretical predictions. Scientists compare these readings with ground-based time measurements to ensure accuracy. The match between theory and observation offers a profound confirmation that gravitational effects on time are consistent, predictable, and measurable across the solar system. Gravity's influence on time also helps explain subtle phenomena in astrophysics. The slowing of time near massive bodies affects orbital dynamics, the behavior of pulsars, and the timing of eclipsing binaries. Researchers measure these variations to test general relativity and improve models of stellar systems. You notice that even abstract observations, like the timing of distant stars, connect back to the same principles that guide the tiny differences detected by clocks on Earth. The universe is organized in a way that allows precise, repeatable measurement of time across scales. Your awareness deepens as you consider that gravitational time dilation links directly to energy. The stronger the gravitational potential, the slower time passes. Clocks near massive planets, stars, or black holes move more slowly relative to those farther away. These effects are cumulative and continuous, demonstrating that time is not simply a backdrop for motion but an active participant in the structure of the universe. Every mass, every gravitational influence, subtly shapes the pace of moments around it. Even at the human scale, you experience evidence of this influence indirectly. Communication signals from satellites, timing of global positioning systems, and corrections applied to scientific experiments all rely on accounting for gravity's effect on time. Without these adjustments, the precision of modern technology would quickly degrade. You feel the connection between observable physics and practical application. Gravitational time dilation is not just a distant phenomenon but a factor in everyday life, quietly shaping systems that you depend upon. Observations of gravitational redshift provide further confirmation. Photons climbing out of gravitational wells lose energy, appearing at longer wavelengths when measured by distant observers. This effect, first measured in experiments on Earth and later confirmed astronomically, illustrates the intimate link between gravity, energy, and the passage of time. You sense that every aspect of physical reality, from light to matter to the ticking of a clock, participates in this interconnected structure of spacetime. You reflect on the steady pull of gravity, now seen not only as a force acting on mass but also as a modulator of time itself. Seconds do not pass at a uniform rate throughout the universe. They depend on the curvature of spacetime created by mass. You feel the quiet elegance of this realization. The flow of time is intertwined with gravity, continuously shaped by the presence of objects large and small. The ordinary moments you experience are subtly linked to the mass of Earth and the cosmos around it, part of a vast, measurable pattern. Your mind lingers on the gentle implications of gravitational time dilation. Even while sitting in stillness, the seconds you perceive are influenced by the unseen curvature of spacetime. You notice that your awareness of time is inseparable from the mass surrounding you, from the planet beneath your feet to the sun above, and even to distant stars. The flow of moments is neither absolute nor uniform but shaped by the distribution of matter in space, a fact confirmed by observation, measurement, and theory. You begin to notice motion in your surroundings, from the gentle sway of trees outside a window to the quiet movement of cars on distant roads. Motion is familiar in everyday life, yet its relationship to time is not immediately apparent. On Earth, speeds are generally low compared with the speed of light, so you rarely perceive time changing due to motion. However, precise measurement and experiments reveal that even motion subtly alters the passage of moments, and this effect becomes significant as speed increases toward the cosmic limit, the speed of light. Einstein's special relativity explains that as an object moves faster, time for it slows relative to a stationary observer. This phenomenon is called time dilation. To imagine this, picture two identical clocks. One remains still while the other travels at high speed. When they are compared after the journey, the moving clock shows less elapsed time. Experiments confirm this prediction, demonstrating that motion is not separate from time but affects it measurably. You sense that time is flexible, responding to velocity in a way that is precise, consistent, and observable. You follow the evidence from particle physics. Particles accelerated to near-light speeds in laboratories decay more slowly than identical particles at rest. Their extended lifetimes are measurable, repeatable, and predictable according to special relativity. These results are not theoretical speculations. They are confirmed by countless experiments using sophisticated detectors and timing instruments. You realize that the flow of time is tied to the speed of objects, and the faster they move, the slower their internal processes appear to an external observer. Satellites and spacecraft provide a real-world demonstration of this effect. Atomic clocks placed aboard orbiting satellites tick more slowly than identical clocks on Earth, due to the combination of their high orbital speed and weaker gravitational field. Engineers account for both velocity-induced and gravitational time dilation to maintain the precision of navigation systems. You notice that the influence of motion on time is subtle but essential, linking abstract theory to tangible applications in technology that guides airplanes, ships, and personal devices across the planet. Your mind lingers on the concept of simultaneity. Events that appear simultaneous to one observer may not be simultaneous to another moving relative to them. Time is not a universal backdrop. It depends on motion and perspective. This principle has been verified in experiments with high-speed clocks, light signals, and synchronized systems moving at different velocities. Each observation reinforces the understanding that motion influences temporal flow in ways that are measurable and predictable, altering the sequence and duration of events in a relative sense. Even ordinary journeys on Earth, though slow relative to light speed, produce effects that are detectable with precise instruments. Aircraft carrying atomic clocks have flown around the globe, with measurements comparing onboard clocks to stationary ones on the ground. These experiments show a tiny but measurable difference, confirming that speed affects time as predicted. You sense that the universe operates consistently, with laws of motion and time applying at every scale, from the smallest laboratory particles to satellites in orbit. You begin to consider the implications for objects moving much faster than human experience allows. As speed approaches the speed of light, time slows dramatically. A spacecraft traveling near this limit would experience minutes while years pass for stationary observers. While such velocities are currently unreachable for humans, the principle is verified continuously in particle accelerators, cosmic rays, and precise timekeeping devices. You feel a quiet fascination in knowing that time is not fixed but stretches and contracts depending on how fast an object moves through space. Length contraction accompanies time dilation. An object in motion appears shorter along the direction of travel when measured by a stationary observer. These two effects, slower ticking clocks and contracted lengths, work together to preserve the constancy of the speed of light. You notice that these consequences are not arbitrary but are required by the structure of spacetime itself. The mathematics of special relativity accurately predicts both phenomena, and observations consistently confirm the predictions, reinforcing the deep connection between motion and time. Light itself provides another avenue for understanding time and speed. A light beam moving in a vacuum travels at a constant speed for all observers. This constancy necessitates adjustments in measurements of both time and space for moving observers. The consequences are subtle at everyday velocities but dramatic at high speeds. You appreciate that these effects are fundamental to the universe's structure, governing the behavior of matter, energy, and information across vast distances. Cosmic rays offer natural examples of time dilation in action. Particles traveling at velocities near the speed of light reach Earth from distant sources, covering distances that should exceed their expected lifetimes. Yet their high speeds extend their decay, allowing them to arrive intact. Observations of these particles match exactly what relativity predicts, demonstrating that motion alone influences the internal passage of time. You feel a quiet connection to these natural experiments, recognizing that the universe continuously validates the principles of relativistic motion. You notice that practical technology relies on these principles, even when the effects are tiny. Particle accelerators, satellite systems, and timing networks all adjust for relativistic effects to ensure precision. The universe's predictable behavior allows humans to measure and compensate for motion-induced time dilation, linking abstract theory to concrete observation. You sense the elegance of this consistency, noticing how the fundamental properties of motion, speed, and time integrate seamlessly into both natural and human design systems. Your awareness deepens as you consider the cumulative nature of these effects. Even small variations in time due to speed become significant over long durations or at higher velocities. A few billionths of a second per second accumulate into measurable differences over days, months, or years. Astronauts traveling in orbit experience this effect, aging slightly less than people on Earth over the same period. You sense the quiet precision of nature, revealing that time's passage is not absolute but dependent on velocity and perspective. Experiments with synchronized clocks moving at different speeds provide repeated confirmation of time dilation. High-speed trains, aircraft, and orbiting satellites all demonstrate consistent changes in the rate of ticking compared to stationary references. These observations verify the predictions of special relativity to extraordinary accuracy. You feel a calm confidence in the laws of physics, knowing that the effect of motion on time is both real and measurable, forming a predictable part of the universe's structure. Even light years away, the principles remain the same. Signals from pulsars, quasars, and other rapidly moving celestial objects reveal timing shifts consistent with relativity. Observations match predictions, whether the motion is terrestrial, orbital, or cosmic. You sense the universality of these rules. Time's flow is influenced by motion at every scale, from atomic particles to entire galaxies. The universe is consistent, measurable, and orderly in its response to speed. You reflect on the subtlety of time dilation in everyday life. Though imperceptible in routine movements, it exists quietly, shaping the behavior of particles, spacecraft, and signals. Each moment experienced on Earth is part of a broader, flexible framework where motion and speed modulate the passage of time. You notice the profound order in this structure, sensing that every second is linked to velocity and motion, forming a consistent and measurable pattern across the cosmos. You settle into the quiet rhythm of your surroundings and begin to consider time as it exists beyond Earth's surface. On the planet you inhabit, seconds pass with familiar regularity. Clocks tick, sunlight moves across the sky, and the rotation of Earth defines day and night. Yet above the surface, where satellites and space stations orbit, the passage of time is subtly altered. Two key influences, gravity and velocity, work together to change the flow of moments, demonstrating that time is not fixed but relative to position and motion. Gravity on Earth's surface is stronger than it is hundreds of kilometers above. The pull you feel beneath your feet is more pronounced than that experienced by a satellite in orbit. Because gravitational time dilation depends on the strength of the gravitational field, clocks closer to Earth tick slightly more slowly than those farther away. Atomic clocks aboard satellites therefore advance more quickly than identical clocks on the ground, a measurable difference confirmed through years of observation and experimentation. You feel the quiet elegance in knowing that the familiar seconds you experience are subtly slower than those floating in the low-gravity environment of orbit. Velocity also plays a critical role. Satellites travel at thousands of kilometers per hour, a motion that induces time dilation according to Einstein's special relativity. High-speed motion causes their clocks to tick more slowly relative to stationary clocks on Earth. This effect partially offsets the acceleration of time due to weaker gravity, creating a delicate balance between two relativistic influences. You notice that both velocity and gravity are fundamental factors shaping the passage of moments, linking the flow of time to physical conditions rather than abstract conventions. Precise measurement is essential for these effects to be observed. Atomic clocks aboard orbiting satellites track the passage of time with extraordinary accuracy. Ground-based scientists compare these readings with identical clocks on Earth, confirming predictions from relativity. The results match theoretical calculations, demonstrating the consistency of physical laws across different environments. You sense that even the most subtle variations in time are predictable and measurable, reinforcing the reliability of scientific observation and the deep interconnection between motion, gravity, and temporal flow. Global navigation systems, such as GPS, provide a practical demonstration of these principles. Satellite clocks must account for both the faster ticking due to weaker gravity and the slower ticking caused by orbital velocity. Engineers apply corrections to ensure that positioning data remains accurate. Without these adjustments, errors would accumulate rapidly, producing navigational discrepancies of kilometers within days. You notice that time's flexibility is not merely an abstract idea but a necessary consideration in systems that guide billions of people every day, a quiet testament to the precision of measurement and the universality of physical laws. The International Space Station offers another illustration. Astronauts aboard experience both the high velocity of orbit and a weaker gravitational field compared to the surface below. Atomic clocks on the station tick at rates that differ slightly from those on Earth, and these differences are monitored continuously. Long-duration missions make these effects more noticeable, with crew members aging marginally less than people remaining on Earth. You sense the tangible reality of relativistic time differences, observing that even in low Earth orbit, the universe enforces measurable, predictable changes in the flow of moments. You notice that these effects are cumulative. A tiny difference in the passage of seconds may seem negligible over a single orbit, but repeated over weeks, months, or years, it becomes measurable. Experiments with synchronized atomic clocks show clear, consistent discrepancies between time in orbit and time on the ground. These findings confirm that time is a physical quantity influenced by environmental conditions, measurable with instruments and predictable through established laws. You feel the subtle reassurance of this consistency, recognizing that the universe behaves with precision, even in ways imperceptible to the senses. Even light, used as a signal between satellites and ground stations, demonstrates time's relativity. Signals are delayed by distance, and their travel is influenced by gravitational potential. Precise timing allows scientists to account for these delays, ensuring that measurements remain accurate. The flow of information itself is intertwined with the flow of time, and you notice that communication, navigation, and observation are all affected by relativity. This connection between measurement and motion underscores the universality of time's behavior, whether near the Earth's surface or in orbit above it. Experiments with clocks in orbit extend beyond low Earth satellites. High-altitude missions, probes to other planets, and deep space observatories all experience variations in gravitational potential and velocity. Atomic clocks aboard these craft provide data used to test relativity across multiple scales. Observations confirm that time dilation and gravitational effects are consistent across different environments, from Earth orbit to interplanetary space. You feel a sense of continuity, realizing that time behaves predictably whether measured on the ground, in orbit, or across the solar system. The practical applications of these observations extend beyond technology. Understanding how time flows differently in orbit allows scientists to design more accurate experiments, coordinate observations of distant astronomical events, and calibrate instruments with extraordinary precision. You notice that the precision of measurement links directly to the reliability of scientific knowledge, revealing a universe that is both predictable and intricately responsive to motion and gravity. Even slight variations in the passage of seconds are detectable and meaningful in this context. Your awareness turns to the cumulative effect on living organisms. Astronauts in orbit experience subtle differences in the passage of time, aging slightly less than people on Earth over the same period. While the effect is extremely small in low Earth orbit, it demonstrates a universal principle. Motion and gravity influence biological and physical processes alike. You notice that the flow of moments around you is connected to your position and movement within gravitational fields, a measurable reality rather than a theoretical abstraction. Time in orbit also provides insight into the interplay between space, gravity, and motion. Both factors combine to shape the ticking of clocks, the timing of signals, and the aging of biological processes. Each observation aligns with the predictions of relativity, offering continuous confirmation of the theory. You sense the quiet elegance of these interactions, noticing that the universe's rules are consistent, measurable, and integrated across scales, from atomic clocks to satellites orbiting hundreds of kilometers above your head. Even as you sit quietly, these principles touch the flow of moments around you. The seconds ticking on your clock are influenced by Earth's gravity and your motion through its surface. The difference between your experience of time and that of an orbiting satellite may be imperceptible, yet it is real and measurable. You sense that every moment is embedded in a complex, physical structure shaped by velocity and gravity, linking your immediate awareness to the broader universe. You reflect on the precise measurements required to detect these effects. Atomic clocks, laser timing, and satellite telemetry allow scientists to observe the subtle differences between earthbound and orbiting time. Each experiment validates predictions made over a century ago, confirming that time is a measurable, flexible dimension. The flow of moments is therefore not universal but dependent on position, velocity, and gravitational influence. You feel the quiet reassurance of this understanding, knowing that the universe behaves consistently and predictably. You sense the interplay of these factors shaping every passing second, connecting the familiar rhythm of life on Earth with the altered cadence of moments in orbit. Even though these differences are subtle, they reveal a universe in which time is dynamic, measurable, and influenced by motion and gravity. The moments you experience are not isolated. They are part of a continuum, shaped by forces and velocities both near and far. You begin by considering the twin paradox, a thought experiment proposed to illustrate the effects of high-speed travel on time. Imagine two identical twins. One remains on Earth, experiencing the familiar rhythm of seconds, minutes, and days. The other travels in a spacecraft at high velocity, approaching a significant fraction of the speed of light. According to the principles of special relativity, the traveling twin experiences time more slowly relative to the twin who stays behind. The difference is measurable, subtle, yet real, and it is not just theory. It has been confirmed in actual experiments. Atomic clocks provide the foundation for this understanding. When scientists send clocks aboard high-speed aircraft or satellites, the traveling instruments tick more slowly than identical clocks on the ground. Over time, these discrepancies accumulate. The results are precisely what special relativity predicts. Motion at high speed affects the passage of time. The analogy to human experience becomes clear. The faster an object moves, the less it ages relative to a stationary observer. You sense the quiet, verifiable truth of this phenomenon, observing that time is not universal but depends on motion and perspective. Astronauts provide a practical illustration of this principle. Crew members aboard the International Space Station orbit Earth at approximately 28,000 kilometers per hour. Their velocity induces a small but measurable time dilation, causing them to age slightly less than people on the planet's surface. The difference is only fractions of a second over months, yet it is real and measurable using ultra-precise clocks. You notice that even tiny variations in time can be detected when instruments are sensitive enough, confirming the predictions made over a century ago. High-energy particle experiments reinforce this understanding. Particles accelerated to near-light speeds live longer than their stationary counterparts. This effect mirrors the twin paradox. Fast-moving particles experience less elapsed time than particles at rest. Observations in particle accelerators consistently confirm the calculations of special relativity. You feel a quiet confidence in these results, knowing that time dilation is not a theoretical abstraction but a measurable property of reality, observable in both human-made and natural systems. You begin to visualize the comparison. On Earth, the twin remains immersed in ordinary routines, their clocks ticking as expected. Above, the traveling twin experiences conditions that stretch the minutes and hours relative to Earth's frame. Signals sent between the twins reveal discrepancies in elapsed time. The difference is not imaginary but the result of precise measurement. You notice that each second is physically influenced by velocity, illustrating the universality of relativistic effects. The passage of time depends on the motion of the observer, and careful measurement allows this to be confirmed repeatedly. Atomic clocks in airplanes have provided striking real-world demonstrations. In one experiment, scientists flew cesium atomic clocks around the world, eastward and westward, comparing their readings with stationary clocks on the ground. The clocks in motion displayed small, measurable differences, perfectly matching predictions from special relativity. These experiments not only confirm the twin paradox but also highlight the precision of modern timekeeping. You notice that the effects are subtle, almost imperceptible without sensitive instruments, yet they demonstrate the reality of motion-induced time dilation. Astronauts returning from space provide another example. Measurements of physiological aging, combined with the data from atomic clocks, indicate that those who traveled at high speed experienced slightly less elapsed time. The differences are small and imperceptible in daily life, yet they provide empirical confirmation of relativistic predictions. You sense that the universe enforces consistency. Time is malleable, motion is influential, and measurement is reliable. The twins, one on Earth and one in orbit, experience the same laws of physics, yet their elapsed time diverges subtly due to velocity. The mathematical description of the effect is precise, though it can be appreciated conceptually without heavy equations. Time dilation depends on the Lorentz factor, which grows as velocity increases relative to the speed of light. Even moderate fractions of light speed produce noticeable, measurable differences when observed over long durations or large distances. You sense the quiet certainty in these calculations. They are not approximations or guesses but precise predictions confirmed by experiments, satellites, and particle observations. Cosmic ray particles offer natural evidence for the twin paradox in action. High-speed particles originating from distant sources reach Earth in greater numbers than expected if they decayed at normal rates. Their extended lifetimes are a direct consequence of moving near light speed, illustrating that motion slows time relative to a stationary observer. These observations occur naturally and independently, reinforcing the principle observed in laboratories and human-made experiments. You notice that nature itself demonstrates relativistic time dilation, linking human understanding to the cosmos. The twin paradox emphasizes that time is relative, not absolute. Each observer measures the passage of time differently based on velocity. While the effect is imperceptible at everyday speeds, it becomes measurable in extreme conditions or with precise instruments. The concept is verified through atomic clocks, satellite telemetry, high-speed particle decay, and cosmic ray measurements. You sense the reassuring consistency of these results. The universe behaves predictably, even when the passage of seconds varies depending on motion. You consider the practical applications of this understanding. Space missions, satellite technology, and high-energy experiments all rely on accounting for time dilation. Engineers and scientists apply corrections to ensure synchronization, navigation, and measurement remain precise. Without acknowledging relativistic effects, systems like GPS would quickly lose accuracy. You notice that the principles of motion and time, once abstract ideas, have tangible consequences in everyday technology and human experience, connecting the high-speed twin scenario to real-world applications. Even the thought of traveling at near-light speeds illustrates the principle clearly. If a spacecraft could approach such velocities, a traveler might experience months or years while decades pass on Earth. Though this remains beyond current human capability, the effect is verified in laboratory and orbital conditions at smaller scales. The universe maintains consistency. Time is influenced by velocity, measurable with precision, and confirmed across independent observations. You sense the quiet elegance in the reliability of these measurements, knowing that the laws of physics apply universally. Your awareness turns to the philosophical implication. The twins experience the same physical reality yet measure time differently. This is not an illusion or imagination but a direct consequence of the structure of spacetime. The combination of motion, measurement, and observation reveals the flexible nature of temporal flow. You notice that each second is not simply a marker of change but a measurable quantity, influenced by the speed at which you move relative to other observers. As you reflect, you recognize that the twin paradox is more than a thought experiment. It is a principle verified through repeated observation, applied to astronauts, atomic clocks, particle physics, and satellites. The discrepancy in elapsed time is measurable, predictable, and consistent with the laws of relativity. You sense the quiet reassurance in this clarity. The flow of time is orderly, comprehensible, and grounded in empirical evidence, connecting human experience with the fundamental structure of the universe. You begin by noticing the presence of gravity as a force you feel every moment on Earth, yet it becomes far more intense near black holes. These regions of extreme mass concentration warp spacetime to extraordinary degrees, influencing the passage of time in ways measurable and precise. A clock positioned near a black hole ticks more slowly than one farther away. This is not a thought experiment alone. Telescopes, satellites, and computer models confirm these effects repeatedly, showing that time itself stretches under intense gravity. Astronomers detect black holes by observing their influence on nearby matter. Stars orbiting an invisible point, high-energy X-rays from infalling gas, and gravitational lensing of background light reveal the mass and location of these objects. Each observation confirms that gravity near a black hole is extreme, bending not only space but the progression of time. You feel a calm clarity in knowing that the very flow of moments is affected by mass, measurable by instruments that detect the precise motion of surrounding matter and light. Clocks near black holes behave according to Einstein's equations of general relativity. The closer a clock is to the event horizon, the slower it runs relative to a distant observer. If you were able to hover just outside the event horizon, you would see time outside accelerate while your own seconds pass slowly. Observational data of orbiting stars and accretion disks provide indirect confirmation of this time dilation. Scientists measure shifts in the frequency of light and signals from matter near the black hole, precisely matching the predicted slowing of time. You notice that this is not speculation but an experimentally supported reality, grounded in measurement and mathematical prediction. Gravitational redshift is one way this effect is observed. Light climbing out of a strong gravitational field loses energy, appearing at longer wavelengths to distant observers. The shift is detectable using spectroscopic measurements, revealing the influence of the black hole's mass on both energy and time. Observations of X-ray binaries and supermassive black holes in distant galaxies confirm that photons from regions near the event horizon reach telescopes shifted exactly as relativity predicts. You feel a gentle reassurance that these extreme effects follow precise, measurable rules, rather than conjecture or abstraction. Simulations of matter falling into black holes also provide insight. High-resolution models track the motion of gas and dust as it approaches the event horizon. The models predict that to a distant observer, infalling matter appears to slow and never quite reaches the horizon, consistent with the severe time dilation predicted by general relativity. These simulations are validated by observational data, including the timing and spectrum of X-ray emissions. You sense the quiet continuity between theory and observation. The slowing of time is not imaginary but a measurable feature of spacetime under extreme gravity. Even though black holes are distant, their influence on time can be compared to subtler effects experienced on Earth. On our planet, gravitational time dilation is tiny, detectable only with atomic clocks, yet near a black hole the effect becomes extreme. Seconds measured close to the event horizon may correspond to years, decades, or longer for a distant observer. You notice that the same physical principles govern both weak and extreme gravity, linking the familiar flow of seconds at home to the intense time dilation of cosmic extremes. Binary systems with black holes provide natural laboratories for studying these effects. When a normal star orbits a black hole, the timing of its motion, eclipses, and emitted radiation can be tracked precisely. Deviations in expected signals reveal the slowing of time near the black hole. Observations from orbiting telescopes and Earth-based instruments confirm the predicted time dilation with remarkable accuracy. You feel a quiet confidence in these measurements, noticing that even phenomena millions of light-years away obey the same physical laws verified in laboratories on Earth. Gravitational lensing offers another observable effect of extreme gravity. Light passing near a massive black hole is bent, and the time it takes for signals to travel is altered. Telescopes measuring multiple images of distant objects behind black holes detect slight delays consistent with general relativity. These measurements provide further confirmation that intense gravity distorts both space and time. You sense that time is intimately tied to the structure of spacetime, continuously shaped by mass and measurable across vast distances. You observe that even orbiting satellites in weaker gravitational fields experience similar principles, though on a much smaller scale. The difference lies in magnitude. Near a black hole, the warping of spacetime is extreme, while on Earth, the curvature is subtle. Yet both cases illustrate the same universal principle. Gravity slows time. You feel a calm understanding of this hierarchy of effects, noticing that the universe obeys consistent rules, from minute laboratory scales to the extreme environments of black holes. Measurements of pulsars near massive objects further support these observations. Pulsars emit highly regular pulses, and when orbiting or passing near black holes, the timing of these signals shifts in accordance with gravitational time dilation. Analysis of these shifts allows astronomers to estimate the mass and gravitational influence of the black hole, demonstrating a direct link between observation and theory. You notice that the slowing of time is not abstract but a measurable influence on the rhythm of light, radio waves, and other signals reaching us across space. Black holes also provide insight into the limits of physics under extreme conditions. Approaching the event horizon, gravitational forces become so strong that time slows to a near halt relative to distant observers. Matter stretches and compresses, and light emitted from these regions appears increasingly redshifted. Observations of high-energy emissions and simulations show this effect clearly. You feel a gentle awareness that even at the extremes, the principles of relativity remain valid, predictable, and measurable, shaping the flow of time in accordance with the mass and energy present. The supermassive black holes at the centers of galaxies offer long-term demonstrations of extreme time dilation. Stars orbiting these giants show subtle deviations in their motion and radiation that reveal the slowing of time in strong gravitational fields. Observations collected over decades match predictions with extraordinary precision, confirming that the universe's behavior is consistent, even in environments vastly different from Earth. You sense the quiet reliability of these principles. Time bends under gravity, yet remains predictable and measurable, governed by the same physical laws across scales. Even though black holes are remote and extreme, their effects on time illustrate a continuum connecting the everyday and the cosmic. From the slow tick of an atomic clock on Earth to the dramatic dilation near an event horizon, the passage of time is influenced by gravity in a consistent, measurable manner. You notice that the familiar seconds you experience are part of this same universal structure, linked to mass and curvature even in the most extreme conditions. Observations of accretion disks, gravitational waves, and relativistic jets provide further confirmation. Each measurement reflects the influence of intense gravity on the flow of time. Signals from matter near black holes are delayed, redshifted, and altered in ways predicted by general relativity. You feel a gentle sense of order, realizing that even the most extreme objects in the universe follow precise, observable laws, shaping the passage of moments in ways that can be measured and understood. You reflect on the implications. Time near a black hole is not just slower, it is dramatically stretched relative to distant observers. This effect is extreme but measurable, confirmed through decades of observation and experimentation. Even in the vast reaches of space, the behavior of time remains consistent with theory, linking the familiar world of Earth to the intense curvature of spacetime near black holes. You begin by noticing tiny particles arriving from space, invisible yet detectable with precise instruments. Cosmic rays, originating from distant supernovae, active galaxies, and other energetic sources, constantly strike Earth's atmosphere. These high-energy particles travel at velocities approaching the speed of light, and their behavior offers direct evidence of how motion influences time. Each particle acts as a tiny experiment, demonstrating principles of relativity in a natural, measurable way. On Earth, most particles of this kind would decay quickly, according to their characteristic lifetimes measured at rest. Muons, for example, are elementary particles created in the upper atmosphere by collisions between cosmic rays and atmospheric nuclei. A muon at rest decays in just 2.2 microseconds. This seems impossibly short to reach the surface, yet muons are detected at the ground consistently. You notice that the universe provides evidence of time dilation through the survival of these rapidly moving particles. The explanation lies in their velocity. Traveling near the speed of light, muons experience time more slowly relative to an observer on Earth. To the muon itself, only microseconds pass, while for stationary instruments on the surface, hundreds of microseconds elapse, allowing the particle to traverse the atmosphere. This is not conjecture but a measured and predictable effect, observed repeatedly in laboratory settings and in natural cosmic ray interactions. You feel a gentle awareness of how nature confirms the principles of relativity through direct observation. Detection of cosmic rays relies on sophisticated instruments, including cloud chambers, scintillators, and arrays of detectors spread over large areas. Each event is recorded with exact timing and energy measurements, allowing scientists to reconstruct the particle's trajectory and lifetime. When muons and other high-energy particles reach the surface, their arrival times and energies match predictions based on special relativity. You sense that each detected particle carries the imprint of relativistic time dilation, a quiet demonstration of physics unfolding naturally across space. High-energy particle accelerators reproduce similar conditions under controlled circumstances. Muons created in accelerator experiments, moving near light speed, also display extended lifetimes compared to stationary muons. Observations match the theoretical predictions with remarkable precision, showing that the slowing of internal clocks with velocity is not limited to cosmic particles but is a fundamental property of matter. You notice that the agreement between natural cosmic rays and laboratory experiments reinforces the universality of these principles. You reflect on the concept of proper time, the interval measured by a clock moving with a particle. For the muon, proper time is extremely short, yet the distance traveled is significant due to its velocity. To an observer on Earth, the elapsed time is longer, demonstrating the relativity of time depending on motion. You sense that the universe operates consistently. Moving clocks tick more slowly from the perspective of stationary observers, whether those clocks are atomic, mechanical, or the internal decay processes of subatomic particles. Cosmic ray observations extend to more massive particles, including pions and other unstable components. Each exhibits longer lifetimes at high velocity, following predictions of special relativity. Measurements collected over decades show remarkable consistency, confirming that relativistic effects are not theoretical but directly observable in natural phenomena. You feel a quiet reassurance in this alignment between prediction and observation, noticing that the behavior of high-energy particles provides continuous, natural verification of time dilation. The detection of cosmic rays also depends on their interaction with the atmosphere. When a high-energy particle collides with atmospheric nuclei, it produces showers of secondary particles that cascade toward the surface. The timing and spread of these showers provide additional data on particle velocities and decay rates. Analysis confirms that the travel distances and lifetimes are consistent only if time dilation is included in calculations. You sense that the universe itself becomes an experimental arena, with cosmic rays offering repeated demonstrations of relativistic principles. Satellite instruments add further precision. Detectors in orbit measure cosmic ray flux before the particles encounter Earth's atmosphere, providing direct readings of their velocity, energy, and decay behavior. These measurements allow comparison with surface observations, confirming that high-speed particles live longer than they would if moving slowly. You notice the continuity between observations made in space and on Earth. Both environments reveal the same physical reality, where motion extends the apparent duration of internal processes. You also consider the historical development of these observations. In the mid-20th century, physicists first noticed that muons reached Earth's surface far more frequently than expected from their known lifetimes at rest. This discrepancy prompted careful investigation, leading to one of the earliest experimental confirmations of special relativity outside the laboratory. You sense that the universe has provided repeated natural experiments, with high-energy particles serving as its own clock to demonstrate that moving time stretches relative to stationary observers. The data from cosmic rays is extensive and reproducible. Arrays of detectors, such as those in high-altitude observatories, continuously monitor incoming particles. Scientists can calculate the particles' velocities and predicted lifetimes, comparing them with the actual number of detections at the surface. The agreement with relativistic predictions is precise, often to within fractions of a percent. You feel the quiet reliability of these observations, recognizing that time dilation is a consistent, measurable effect verified by both natural and experimental means. Even the highest energy particles traveling across interstellar distances demonstrate the same principle. Cosmic rays generated in supernova remnants or other distant phenomena maintain their velocities for light years, allowing them to arrive at Earth intact. Without time dilation, these particles would decay long before reaching the planet. The observations reveal that time for these fast-moving particles is stretched, permitting survival across vast distances. You notice that the universe provides both the laboratory and the evidence, confirming the same laws of physics across cosmic scales. You reflect on the broader meaning. The passage of time is intimately tied to motion. Particles moving near light speed experience seconds and microseconds differently from stationary observers. This is not an abstract idea but a fact measurable in natural and artificial systems alike. Each detection, each recorded event, is a small testament to the malleability of time, showing that the universe measures duration relative to velocity consistently and predictably. Cosmic rays also link to other relativistic phenomena you have encountered, including the twin paradox and time differences in orbiting satellites. Together, these observations reinforce the principle that time is flexible, affected by velocity and gravity, and measurable with precise instruments. You sense a calm order in this network of evidence, noticing that the behavior of high-speed particles, clocks, and observers all align seamlessly with the predictions of relativity. You notice that these tiny, high-energy travelers are more than just particles. They are evidence that the universe behaves consistently across scales and contexts. Each muon reaching Earth demonstrates the slowing of time in motion, connecting the laboratory, cosmic rays, satellites, and human understanding into a coherent, verifiable picture. You sense the quiet continuity of nature's laws, unchanging yet observable in subtle and profound ways. Even as you rest, the high-speed particles continue their journey from distant sources, carrying the imprint of relativistic time. Their lifetimes, extended by velocity, quietly confirm the structure of spacetime and the predictable influence of motion on temporal progression. You feel a gentle connection to the universe's precision, noticing that each moment, for particles and observers alike, is shaped by movement and measurable with clarity. You begin by noticing that time is not just a theoretical concept but something that guides everyday life. Your smartphone, your car's navigation system, and even emergency services rely on precise timing to function correctly. At the heart of these systems is the Global Positioning System, a network of satellites orbiting Earth, each equipped with extremely accurate atomic clocks. The accuracy of these clocks is essential because even a tiny misalignment in time could produce significant errors in determining location. Satellites orbit Earth at altitudes around 20,200 kilometers, moving at speeds of approximately 14,000 kilometers per hour. At these velocities, relativistic effects become measurable. Special relativity predicts that moving clocks tick slightly more slowly relative to stationary clocks on Earth. At the same time, general relativity predicts that clocks further from Earth's gravitational field tick faster than those on the surface. The combination of these two effects influences the satellite's clocks in opposite ways, and both must be accounted for to ensure proper synchronization. You notice that the net effect is significant. Without corrections for both gravitational and velocity-induced time dilation, positioning errors would accumulate at a rate of about 10 kilometers per day. This would render the system useless for navigation. Engineers incorporate relativistic corrections into both the design of the satellite clocks and the algorithms that translate their signals into positions on the ground. You feel a quiet reassurance that abstract physical principles have direct, practical consequences for everyday life. Each GPS satellite contains multiple atomic clocks, often cesium or rubidium, which maintain extraordinary precision. These clocks are synchronized before launch, but once in orbit, both the weaker gravity and the high speed of the satellite cause their ticking to deviate from ground-based clocks. The difference is measurable. Gravitational time dilation causes satellite clocks to tick faster by about 45 microseconds per day, while velocity-based time dilation slows them by about 7 microseconds per day. The combined net effect is a faster ticking rate of approximately 38 microseconds daily, which is continuously corrected. You notice the precision required. Even microsecond-level errors matter when translating signals into physical distance. Time is transmitted from satellites using radio signals, which carry the information of the exact moment the signal was emitted. Receivers on Earth measure the arrival time and calculate distance based on the speed of light. Because the speed of light is constant, timing accuracy translates directly into spatial accuracy. Relativistic time corrections are built into the system's software to account for differences between satellite and ground clocks. You feel the elegance of this integration. Theory and technology work together seamlessly to maintain accurate measurements across thousands of kilometers. Even small errors in clock timing would have measurable consequences. For example, a discrepancy of 1 microsecond corresponds to a positional error of approximately 300 meters. The satellite's clocks must therefore remain synchronized not only with one another but also with ground-based reference clocks. Continuous monitoring and correction ensure that the system functions reliably. You notice that relativity is not an abstract idea in this context but a practical requirement for precision technology in everyday life. The corrections for relativistic effects are not static. Orbital perturbations, variations in Earth's gravitational field, and even temperature changes affect the clocks. Engineers continuously update satellite data and maintain synchronization with ground stations. The accuracy of the system relies on a feedback loop between observation, measurement, and correction. You feel the quiet sophistication of the design, recognizing that it is the application of physics principles to a real-world, high-precision technology. The GPS system also provides a unique confirmation of relativistic effects. When signals from satellites are analyzed over time, the differences in elapsed time match predictions from general and special relativity. Measurements of signal timing, orbital motion, and gravitational influence all align with theory, providing ongoing verification that time dilation is not merely theoretical, but a measurable phenomenon affecting technology. You notice that the everyday functioning of navigation systems quietly confirms the principles of physics in a tangible way. Even for people unaware of these corrections, the impact is profound. When you use a navigation app to locate a destination, the coordinates rely on satellites that are corrected for relativistic time differences. The system provides accuracy within meters, a result entirely dependent on the proper functioning of atomic clocks and the application of relativity. You sense the subtle yet profound connection between abstract physical laws and the practical convenience of daily life. The understanding of time dilation in GPS satellites also informs other space missions. Spacecraft navigating around Earth, the Moon, or other planets must account for variations in time due to velocity and gravitational potential. Communication signals, trajectory calculations, and onboard systems rely on accurate timekeeping to function correctly. You notice that relativity is embedded in multiple layers of modern technology, from everyday navigation to deep space exploration, connecting human experience to universal physical principles. Atomic clocks aboard GPS satellites have undergone continuous improvement since the system's inception. The development of more stable and precise clocks reduces errors and increases reliability. Each generation of satellite improves measurement accuracy, reflecting both technological innovation and a deeper understanding of the physical principles governing time. You feel the quiet satisfaction of observing human ingenuity applying verified science to maintain precision in complex, real-world systems. Time in GPS systems also demonstrates the universality of relativity. Signals travel through space, subject to both velocity effects and variations in gravitational potential. Observers on Earth experience different elapsed times compared to the satellites, yet all measurements reconcile with theory. The system continuously adjusts to ensure that positions calculated from signals are accurate. You notice that this is not coincidence but a reflection of the consistent, predictable behavior of spacetime, measurable and observable in our technological environment. You consider the role of satellites as clocks in motion. Their velocities and distances from Earth create a measurable divergence in elapsed time. The system compensates for these divergences automatically, ensuring that every measurement of location is reliable. Without these relativistic corrections, the system would fail, demonstrating that time dilation is not only observable but practically consequential. You sense the quiet integration of theory and practice, where the abstract principles of physics manifest in tangible, everyday applications. Even the signal travel time is accounted for. Since the radio waves move at the speed of light, differences in distance between satellites and receivers create additional delays that must be precisely measured. This interaction between light, motion, and gravity further confirms the necessity of relativistic corrections. You notice that these adjustments, though imperceptible in daily life, are vital for the system's remarkable accuracy. The network of GPS satellites illustrates a continuous feedback between observation, theory, and application. Each satellite acts as a moving clock, its signals monitored and corrected, demonstrating the effects of velocity and gravity on time. You feel the quiet assurance that physical laws are not only consistent but directly applicable, providing both theoretical and practical verification of relativity. Even as you rest in awareness, the satellites orbit silently, their atomic clocks ticking in alignment with the laws of physics. Each signal they send carries evidence of gravitational and velocity-induced time dilation, connecting human technology to the fundamental structure of spacetime. You sense that the flow of time in everyday life is entwined with these precise measurements, a constant, gentle confirmation of the principles that govern both the universe and the tools you use. You begin by noticing that time has a direction, a consistent flow from past to future, observed in the everyday progression of events. The universe itself exhibits this directionality on a cosmic scale. Entropy, a measure of disorder in a system, increases over time, providing a statistical arrow that points from less probable states to more probable ones. This principle, rooted in thermodynamics, is measurable and universal, influencing everything from microscopic interactions to the evolution of galaxies. Observations of the cosmic microwave background reveal a universe that began in a hot, dense, and highly ordered state nearly 13.8 billion years ago. This radiation, now cooled to just a few degrees above absolute zero, carries the imprint of the early universe's structure. Tiny fluctuations in temperature reflect variations in density that seeded the formation of stars and galaxies. You sense the continuity of time through these observations. The universe has a record of its own past, encoded in measurable radiation that still reaches us. You notice that the expansion of the universe itself provides a framework for understanding the flow of time. Space is not static. Galaxies move apart from one another, and the rate of expansion can be quantified using redshift measurements. The observation that light from distant galaxies is stretched to longer wavelengths allows astronomers to calculate how far away these objects are and how long the light has been traveling. This provides a temporal map of cosmic history, showing that time and space are interconnected. Entropy continues to increase as stars burn fuel, matter coalesces into planets, and black holes form. You observe that the arrow of time is linked to energy transformations and the dispersal of heat. Each process, from the fusion in a star's core to the decay of radioactive isotopes, occurs in a manner consistent with increasing entropy. You notice that the same physical principles apply universally, providing a measurable, predictable sense of the forward progression of time. Galaxy evolution provides another illustration of time's direction. Young galaxies contain abundant gas, forming stars at high rates. Older galaxies exhibit less gas and more evolved stars, with structure and composition reflecting billions of years of development. Observations using telescopes like Hubble and the Atacama Large Millimeter Array reveal detailed histories of these systems, confirming that the universe progresses in a temporal order, measurable through changes in structure, chemical composition, and radiation output. Gravitational interactions also demonstrate the forward direction of time. Stars orbit in galaxies, clusters of galaxies move relative to one another, and cosmic filaments stretch across vast regions of space. Each motion follows predictable laws of physics, resulting in a statistical increase in disorder on a large scale. Collisions, mergers, and accretion processes contribute to entropy, revealing that time's arrow is not merely abstract but grounded in measurable phenomena. You sense that every movement of matter reflects the unidirectional flow of time, connecting local processes to cosmic evolution. Black holes further illustrate the link between gravity and entropy. According to observations and theoretical models, black holes possess entropy proportional to the area of their event horizons. Matter falling into a black hole increases this entropy, providing a measurable connection between gravitational systems and the arrow of time. Signals from accretion disks and relativistic jets demonstrate energy release and mass distribution changes, reinforcing the idea that time moves forward in a consistent, observable manner, even in extreme environments. You notice that cosmic expansion, entropy increase, and structure formation all converge to define a universal directionality. The arrow of time is not simply a human perception but a measurable property of the cosmos. Observations from microwave background measurements, galaxy surveys, and large-scale simulations consistently support the same conclusion. Time progresses from ordered initial conditions toward states of greater disorder, and this progression is quantifiable. Entropy's role in microscopic processes is equally observable. Individual atoms, molecules, and particles interact according to probabilistic laws, and over time, these interactions contribute to macroscopic disorder. Experiments with gases, diffusion, and heat transfer provide laboratory-scale verification of the same principle governing the cosmos. You sense a continuous link between small-scale physical interactions and the evolution of the universe, noticing that time's arrow is consistent across scales. You reflect on the relationship between entropy and relativity. While special and general relativity describe how time can be experienced differently depending on motion and gravity, the thermodynamic arrow of time provides a universal direction independent of these variations. Clocks in motion or near massive objects may tick differently, yet the statistical progression toward higher entropy remains consistent, offering a complementary perspective on temporal flow. The observation of distant supernovae also illustrates the arrow of time. Exploding stars release energy, create heavy elements, and enrich interstellar space. The remnants of these events, from expanding gas clouds to neutron stars, can be observed and timed precisely. Analysis shows predictable sequences of nuclear reactions and energy dispersal, reflecting the irreversible nature of these processes. You notice that the forward flow of time is embedded in the life cycle of stars and in the chemical evolution of galaxies. Even at the scale of planetary systems, the arrow of time is measurable. Planetary orbits evolve due to gravitational interactions, tides dissipate energy, and atmospheres change composition over billions of years. These changes are observable and consistent with an overall increase in entropy, demonstrating that time's progression is measurable even within relatively small systems compared to the universe. You feel the quiet reassurance that time moves predictably, from microphysical processes to the motion of planets and stars. The cosmic microwave background provides a long-term record of the universe's thermodynamic history. Measurements of its temperature and uniformity reveal how energy distribution has evolved since the earliest moments after the Big Bang. Tiny anisotropies in the radiation allow reconstruction of the formation of large-scale structures and provide precise constraints on the expansion rate and overall mass-energy content. You notice that these measurements not only confirm the universe's past but also reinforce the understanding of time's arrow on cosmological scales. Large-scale structure surveys complement these observations. By mapping the distribution of galaxies, clusters, and voids, astronomers can trace the growth of cosmic structure over billions of years. Computer simulations of cosmic evolution, guided by general relativity and observed density fluctuations, reproduce the statistical properties of the universe remarkably well. These studies reveal a measurable pattern of increasing complexity and disorder, providing additional evidence of time's unidirectional progression. You reflect on the subtle relationship between entropy and the flow of events you experience daily. From the formation of clouds to the melting of ice, local processes are aligned with the same universal principles governing stars and galaxies. Each increase in disorder is a small echo of the larger cosmic pattern, observable, predictable, and consistent. You sense that the arrow of time links every scale of nature, connecting human experience to the evolution of the universe. Even the expansion of space itself is tied to temporal progression. Redshift measurements reveal that galaxies recede at rates proportional to their distance, providing a measurable indicator of the universe's ongoing evolution. Observations from the Hubble Space Telescope, ground-based observatories, and cosmic microwave background studies all confirm the same conclusion. The universe moves forward in both time and space, with measurable changes in structure, energy distribution, and motion. You notice that the arrow of time is both a principle of physics and a practical tool for understanding cosmic history. By observing entropy, expansion, and structure formation, scientists reconstruct past events and predict future trends. The flow of time is measurable, consistent, and observable across scales ranging from the smallest particles to the largest galaxy clusters. You sense the quiet reliability of this principle, noticing that time's direction is embedded in both local and cosmic processes. You begin by noticing your own heartbeat, the steady rhythm marking the passage of time within your body. Biological processes, from cell division to metabolic cycles, follow a temporal rhythm that is familiar and consistent on Earth. Yet when humans travel at high speeds or experience different gravitational environments, subtle changes in the timing of these processes can occur. Observations from astronauts provide measurable examples of how relativity influences living systems. In low Earth orbit, astronauts travel at velocities around 28,000 kilometers per hour. At this speed, time dilation according to special relativity is small but real. Their clocks tick slightly slower relative to those on Earth, and the difference, though measured in milliseconds over days or months, is detectable. You sense the quiet reality that even within living organisms, the passage of time can be influenced by motion. Precise monitoring of astronauts' physiological data allows scientists to compare biological aging with elapsed time on Earth. Cell replication rates, circadian rhythms, and other temporal markers are tracked before, during, and after missions. Studies confirm that astronauts age slightly less from the perspective of a stationary observer on Earth, consistent with the predictions of relativity. You feel the gentle precision of these measurements, recognizing that time is not merely abstract but interacts with life in measurable ways. Biological systems also respond to microgravity in ways that indirectly reflect temporal experience. Muscle atrophy, bone density changes, and cardiovascular adaptation occur gradually and are tracked carefully. Although these effects are not caused by time dilation, they influence the overall perception of aging and physical development. You notice that even subtle environmental changes provide a framework for understanding how living systems experience time differently in space. Molecular processes can be used as indicators of temporal progression. Telomeres, the protective caps at the ends of chromosomes, shorten with cellular replication. By measuring telomere length before and after space missions, researchers gain insight into the pace of biological aging. Observations reveal that telomere shortening in astronauts aligns closely with the predicted effects of microgravity, radiation exposure, and relativistic time dilation, offering a nuanced picture of how life adapts to space. You feel the quiet consistency of these measurements with fundamental physics. Circadian rhythms, the natural cycles of sleep, hormone production, and metabolism, also provide a measure of temporal flow in living organisms. In orbit, the day-night cycle is compressed, with the International Space Station experiencing a sunrise and sunset approximately every 90 minutes. Astronauts' internal clocks adjust, yet remain measurable against Earth-based standards. These rhythms illustrate the interplay between biological time and physical time, showing that living organisms are finely attuned to their temporal environment. Experiments using blood markers, hormone levels, and metabolic rates reveal small discrepancies between Earth-based and space-based timekeeping. While these differences are subtle, they are consistent with the minor time dilation predicted by relativity. For long-duration missions, such as stays on the International Space Station, these measurements accumulate, providing an empirical record of how living systems experience time differently when moving at high speeds. You sense the continuity between physical laws and biological processes, noticing that relativity subtly influences life. Radiation exposure in space adds another factor influencing biological aging. Cosmic rays and high-energy particles interact with cells, sometimes damaging DNA and influencing cellular repair mechanisms. Scientists track these effects using precise dosimetry and biological assays. Although these processes are independent of relativistic time dilation, they combine with motion-induced temporal effects to create a measurable profile of how organisms age in space. You feel the calm precision of this combined understanding, recognizing that multiple measurable factors influence biological time beyond Earth. Sleep studies conducted in orbit reveal further evidence of temporal adaptation. Astronauts use scheduled light exposure, controlled environments, and monitoring devices to maintain circadian alignment. Differences in sleep onset, duration, and efficiency provide additional data on how biological clocks respond to the unique conditions of space. These observations reinforce the understanding that time, while universal, is experienced differently depending on motion, gravity, and environmental conditions. Experiments using model organisms, such as fruit flies and mice, provide additional verification of relativistic and environmental effects on biological aging. High-speed flights, simulated microgravity, and controlled radiation exposure allow scientists to measure lifespans and physiological changes relative to Earth-bound controls. Data consistently show slight differences in timing and cellular processes, supporting the conclusion that relativistic effects, though subtle, are detectable in living systems. You notice that even the smallest life forms provide measurable confirmation of time dilation's influence on biology. Long-duration missions offer the clearest measurements. When astronauts return from months in orbit, scientists compare physiological markers, DNA replication rates, and other temporal indicators against Earth-based controls. Slight differences in elapsed biological time correspond with the predicted effects of velocity-induced time dilation. These observations provide direct evidence that relativity is not confined to clocks or particles but extends to living organisms. You feel a gentle sense of connection between abstract physical principles and tangible biological outcomes. Space agencies continuously refine their understanding of time's influence on life. New instruments, advanced monitoring systems, and longer missions provide increasingly precise data on the interaction between biology and relativistic time. Each dataset confirms that time experienced by living organisms in motion differs in measurable ways from that experienced on the stationary surface of Earth. You sense the quiet reliability of these results, understanding that the universe's laws apply equally to physics and biology. You notice that even in the subtle differences observed, the fundamental processes of life continue without disruption. Cells divide, organisms metabolize energy, and biological rhythms persist, all in alignment with the predictable effects of relativity. Time dilation does not halt life but slightly adjusts the pace relative to stationary observers. This demonstrates the universality of physical laws, gently bridging the gap between the motion of spacecraft and the flow of biological systems. The cumulative effect of these observations is a calm understanding that time is not uniform for all observers, living or otherwise. Relativistic principles extend beyond atomic clocks and particles, influencing physiological processes in subtle, measurable ways. Astronauts returning from orbit provide living evidence of this effect, connecting theoretical physics to everyday biological reality. You sense a quiet wonder in observing that the passage of time, for both humans and particles, depends on motion, yet remains predictable and measurable. Even as life on Earth continues at a steady pace, astronauts' experiences reveal the malleability of time for those in motion. Measurements of heart rate, cellular division, circadian alignment, and molecular aging all confirm the interplay between physics and biology. You notice that these subtle variations, though small, are entirely consistent with the predictions of Einstein's theories, demonstrating that relativity quietly shapes life in the cosmos. You begin by noticing the steady rhythm of time around you, the same seconds and minutes that have guided your observations throughout your journey. You carry with you the knowledge that time is not absolute but flexible, shaped by motion, gravity, and energy. Every clock, from the atomic timepieces in satellites to the natural oscillations within your own cells, measures a passage that can vary depending on circumstances. You feel the continuity of this understanding as you imagine moving from one frame of reference to another, gently observing the differences in elapsed time. As you return from space to Earth, you consider the effects of velocity on your own experience of time. High-speed travel produces small but measurable differences, as seen in the twin paradox and confirmed by astronaut observations. The clock you carry, along with your biological rhythms, has ticked slightly differently from those that remained on Earth. You sense that these variations, though minute, are real, and that nature itself records the influence of motion on the passage of moments. Gravity too shapes your temporal experience. When in orbit, you have been farther from Earth's gravitational well, and your internal clock has ticked slightly faster relative to one on the surface. You recall that GPS satellites must correct for this effect to maintain precision. The combination of motion and gravitational influence demonstrates that time is a dynamic quantity, measurable and predictable, rather than a static backdrop against which events occur. You notice that the universe has provided multiple, consistent ways to observe these effects. As you descend toward Earth, the familiar environment serves as a reference. Your mind notices subtle cues: the progression of shadows, the motion of clouds, and the changes in temperature and air pressure. Each of these phenomena unfolds in accordance with ordinary timing, yet you are aware that the passage of seconds for you has been slightly different from those who remain stationary. This awareness is not abstract but rooted in measurable physics, connecting your subjective experience to the precise predictions of relativity. Astronauts returning from long-duration missions show small, verifiable differences in elapsed time relative to people who remained on the ground. Laboratory experiments with particles and atomic clocks corroborate these observations. Even biological markers, such as circadian rhythms and molecular aging, align with predictions based on motion and gravity. You sense the quiet coherence of these results. The universe behaves consistently, whether measured by particles, technology, or living systems. The journey through relativistic time has also revealed the universality of physical laws. From muons reaching Earth's surface to satellites maintaining precise synchronization, each observation demonstrates the same underlying principles. The passage of time is influenced by speed and gravity, yet remains predictable and measurable. You feel the calm order of these interactions, noticing that the flow of time is continuous, connected across space, and observable in countless ways. Observing Earth from above, you notice the planet's rotation and orbit, marking time in the familiar cycles of day and year. These rhythms are regular but only approximate the absolute passage of time. The fine details, such as the slowing of a clock in motion or the extended life of high-speed particles, remind you that time is relative, not uniform. You sense that the ordinary progression of seconds and minutes is layered upon a deeper, more intricate temporal structure, measurable with scientific instruments and reflected in your experience. You reflect on gravitational time dilation near massive bodies. Clocks closer to Earth's surface tick more slowly than those in orbit. This is measurable and has practical consequences for navigation and communication. You notice the precision required for such measurements. Even microseconds matter, yet the effects are entirely predictable. The universe provides a laboratory in which these principles operate continuously, allowing observations that connect theory with practice. The concept of time as a flexible dimension also extends to cosmic scales. Light from distant stars and galaxies takes millions or even billions of years to reach you, carrying information about the past. Observing these signals allows reconstruction of cosmic history, revealing the expansion of space and the formation of structures. You sense the interconnection between your personal experience and the vast timeline of the universe, noticing that the same laws govern both local motion and the evolution of galaxies. Cosmic rays continue to demonstrate relativistic effects even as you settle back on Earth. Particles moving near light speed live longer than expected, confirming that time stretches with velocity. These observations complement those from satellites and biological studies, reinforcing a consistent picture in which time is dynamic and measurable. You feel the quiet elegance of this principle, observable across scales from subatomic particles to entire galaxies. You notice that your own biological rhythms are now closely aligned with Earth's frame of reference. Circadian cycles, heartbeats, and cellular processes follow familiar timing, yet you carry the subtle imprint of your journey. The minor differences in elapsed time, though imperceptible without precise instruments, are real and consistent with predictions. You sense that life continues predictably, guided by physical laws, even when experienced under different gravitational or velocity conditions. Time's passage is also reflected in entropy, the universal trend toward increasing disorder. On Earth, you observe local processes such as melting ice, flowing water, and chemical reactions. On cosmic scales, stars fuse elements, galaxies evolve, and black holes accumulate mass, all illustrating a directional flow of time. You feel the connection between microscopic and macroscopic processes, noticing that the arrow of time provides a coherent, measurable progression from past to future. Even as you return to familiar surroundings, the knowledge of relativistic effects persists. Satellites continue their orbit, atomic clocks tick in synchrony, and cosmic particles journey through space, all consistent with the principles you have observed. You sense the subtle harmony between your everyday experience and the broader universe, where motion, gravity, and energy shape the passage of moments in predictable ways. The understanding you have gained also emphasizes the practical importance of precise time measurement. Navigation, communication, and scientific observation all rely on accurate clocks and corrections for motion and gravity. Technology on Earth integrates these principles seamlessly, making relativity an invisible yet essential part of daily life. You notice that the universe's laws are not distant abstractions but active participants in human activity, measurable, reliable, and continuous. You reflect on the journey as a whole, observing that every experience of time is relative, whether for subatomic particles, satellites, astronauts, or yourself. Measurements, predictions, and observations align across different contexts, creating a coherent understanding of temporal flow. You feel the quiet satisfaction of knowing that time is both measurable and malleable, consistent yet dependent on circumstances, and fundamentally connected to the universe's structure. Even in rest, your mind carries the understanding of these principles. The flow of time you perceive on Earth is intertwined with velocity, gravity, and cosmic evolution. Each second, minute, and hour reflects both your local frame of reference and the broader, predictable behavior of the universe. You sense the continuity of these processes, noticing that time itself is a measured and observable phenomenon, influencing life, technology, and cosmic structures alike.